This is Egon Elbre. He is from Estonia. He has over 10 years of experience, and his focus is on maintainable and understandable code that delivers value. He also draws and plays the piano. His talk will be on a tale of performance breadth first search, which is a topic, at least breadth first search is a topic pretty much everyone who has been to university is familiar with, from algorithm class at least, or something. And yeah, he also gave a talk in the previous GopherCon, a very good one. And yeah, without further ado.
Okay, thank you, Paul. So today we are going to talk about optimization and performance. Few disclaimers first. I won't explain all of the details. It's fine if you miss some of them. They go step by step and build up. They don't build up on each other, but they are kind of individual ideas. Don't worry about the exact numbers or the exact code. There will be a link to a fuller description of what happens. Try to understand the overall process instead, because I think that's the more valuable thing to get out of here. Disclaimer number 2, 95% of the code won't need this. I think it's a nice balance, because last year I talked about code readability. Now I'm going to talk how to destroy your code readability. And disclaimer number 3, there's no third disclaimer, just in case. So how do we optimize code? There's actually a really simple idea how to do it. First, you measure what you're doing. If you don't measure, you're guessing, and you don't really know what the processor is doing and how the computer is behaving exactly. Then you try to guess why it's behaving that way, like why it's taking so much time in a particular place. Then you try to guess, what could I do to fix those? And then you test them, all of them, and see what happens. And then you'll keep the best solution, just in case, keep around the second best and kind of some of the other ideas, and then you repeat it. This actually doesn't require any prior knowledge. However, it can definitely help, because knowing the tools to make your measurements easier, knowing different theories, of course, makes it easier to figure out new hypotheses. And so, how to get knowledge? There's a performance Slack channel. There's 2 books I recommend: Algorithm Design Manual by Steven Schiena, and a Go-specific one is GopherCon book by Damian, who also hangs out at the performance channel. And the basic ideas I'm going to cover are these. First, use better algorithms. This is kind of obvious. If you do less work, then your code will work faster. Make it predictable, which means that you don't want to leave the processor guessing what you're going to do next, but instead make it as linear as possible, make it do sequential things, so there's no ifs and elses anywhere. Use less memory, because when you have using less memory, which means that you're going to communicate with the memory chips less. And use fewer pointers, because pointers can kind of put data in the wrong place where you don't want them. And keep computations close, which means that when you're computing on some data, you don't want to spread it over a large span of code, but instead keep it local to the place you're computing. And yeah, those are the basic ideas. And quick overview, what was breadth first search, in case you have forgotten it. So our tail starts at performance Slack channel, like all nice performance tails do. So there was a question about why is Go code being slower than C code. And we're seeing that initially the C code was doing 26 seconds and the Go code was 80 seconds. However, I would expect that Go will be about a factor of 2 of at most, so around 50 seconds. So there's definitely something that could be improved. So what is the dataset that we are working with? It's a so-called tiny dataset and social network with 65 million nodes and 1.8 billion edges. So quite a few nodes. Okay, so this is a graph. Let's say these are people and how they connect with each other. Breadth first search tries to iterate through the graph such that every level at a time, one level at a time. So if we start from A, we'll next want to visit all the people who are one connection away from you, and then 2 connections away from you, and then 3 connections away. So you kind of go through each one of here. And let's get the starting code. So this is what's the pseudocode version of breadth first search, how it usually is written. We have a set of nodes that we have already visited. So we know that we don't backtrack into higher levels. And we also have the current level that we are currently iterating over, and the next level that we want to iterate on the next kind of phase. And then we loop over each node in the level we are currently inspecting. Then we'll visit all the neighbors of that node and see whether we have already visited it. If we haven't, then we'll add it to the next level and the visited set, so we don't visit. So we'll visit them on the next iteration, right? And the equivalent Go code in this case would be something like this. Well, of course, we'll make a visited set. We'll have the current and next level, which are slices. And we'll make the first visited set, and then we'll do the iteration over the current level, visiting the neighbors, and so on. So it's pretty much the same code. We already have some optimizations here in place for not allocating the levels multiple times. However, yeah. Also, one of the things is that we also need a compact representation of the graph. So the initial code already had this optimization in place, which is a compact adjacency list, which means that instead of using pointers here for pointing to different nodes, we'll use an index into a different list to find the neighbors for a given node. So if here's 2, so here's 2 to 4, so B's neighbors will be between indexes 2 and 4 here, so A and C. You might be asking why not use pointers here. So the implementation, of course, isn't too complicated for some definition of complicated. So why not pointers? Let's do a quick back of the envelope calculation. So here we'll have number of nodes times 24 bytes, which is the size of the slice here, and the number of edges, which is these pointers here. And in the compact list, we have the number of edges times 4 bytes for each of the indexes, and the span is 8 bytes, so UN64 plus the slice sizes. So if we calculate this, we'll get that this compact adjacency list is 7 gigabytes of RAM and this pointer-based solution is 15.9 gigabytes. So it's 2 times difference between the amount of RAM used. Great. Now we can actually start. This is our baseline measurement. You read this as the left side is on my local laptop, which was a small machine. On the right is a 648-core NUMA machine. So these are using different scales. So I'm locally using 5 million nodes, and the bigger machine is using 65 million nodes. So let's try the easy things first. One of the major bottlenecks can be that you're checking whether the neighbor is in this bounds here. So you can disable bounds check. I wouldn't recommend it for production. However, it gives us a good indicator whether we are bound by bounds check. Yes. And I didn't get any significant difference, which means that I don't need to start worrying about whether bounds are being eliminated or not, because apparently it doesn't make a difference in this case. The next thing is try the latest Go version or the next release. Maybe if we just wait a bit, we don't have to actually optimize. So it was, at that time, it was 10% faster, which meant that, yay, if we wait for 6 months, we'll get 10% faster code. So let's look at our code. One of the things that you notice here is that we have this assignment for on which level each neighbor is. And we also check whether we have visited the neighbor. However, why have 2 data structures when we could use both? Because when the appropriate layer or level isn't assigned, we can check it from there. So a little experiment later, let's replace it whether we have assigned it the level. We get this results, yay, 10% faster, right? So, and if we repeat the measurement for the large result, we get 2 times lower. Damn it. So this is a good introduction into how performance optimization really works. You have an idea and it fails multiple times, or different ideas as well. So apparently memory is a real thing. Because we started using the larger data structure for storing the levels, it didn't fit into any of these nice little caches near the processor and made it slower. However, it did make it faster for a smaller data set. So in some sense, you cannot optimize for all different data. You need to pick a particular data set that you're interested in and optimize for those cases more rather than any random case. Of course, we need to measure things. One of the things I noticed is that this neighbor's iteration here was taking too long. I was wondering, like, why? Why would it do that? And then I realized that how this current level, like the nodes in this, the nodes that we are iterating over could be in a random order. So, which means that we are randomly accessing these nodes in this big 8 gigabyte slice. So what can we do? Let's sort things. So let's sort the nodes before we iterate over them. And as a result, really small difference. However, this made me happy because I know that sort slice isn't particularly optimized for really small types, or I guess because it uses the sorting through an interface. So what I did, optimize the sorting function for uint32, and I got that 20% improvement compared to the baseline. And of course, there are plenty of bright people at performance channel, and Damian suggested to use radix sort, which gave another 5% improvement. Okay, now we are progressing at least. So the other thing I noticed is that if this neighbor is in random order, this means that this assignment is also in this random order. So we would like to make it linear as well. We could actually move this level assignment after the loop, because we had the whole collection and we already do the sorting, so we can assign the level incrementally, right? And this gave me 10% improvement, roughly speaking. And still, the next thing I was looking at, it was this visited state was slow. So can we optimize here something? So one of the things I noticed here is that this visited contains and visited add are related computations. So what if I move them closer? So in this case, the visited contains and visited add are immediately after each other. So there isn't probably the processor could potentially improve the performance in that sense. So that gave me 10% improvement from ordering the lines differently. So there's also this part of assignments that we might want to fuse two operations into a single one of contains check and adding to the node set. Maybe we can fuse it into a single function that performs faster. I also tried two different versions of it. One is using bit operations to assign every time, and the other using a regular if statement. Depending on the situation, one might be faster than the other. And no luck, so pretty much the same thing. And right, so maybe we can avoid this visited check altogether by not checking it completely later. And that was a complete failure. The next level that it built ended up being 10 times larger, which was really bad for the sorting and removing the items. And so, yeah, bad idea. But still, I heard about data structures like Cuckoo filter and Bloom filter. And so I was thinking, like, what if we replace the bit set with one of those? Let's see what happens. Terrible idea number 2. So it went 20 times slower. Unfortunately, the slides didn't fit the actual numbers here. So, but you can imagine how bad it is, because it should be 10 times larger than this bar here. So from your monitor, I guess 5 monitors into the distance. So I was thinking, what can we do more? Maybe we can unroll our loops, which means that bringing closer the accessing the data from these lists and then operating on the set structure, so we don't always do this stepwise, right? Or each loop we don't pick only one node to inspect, but we inspect multiple at a time. And there was a 5% improvement, because also there were different ways of unrolling the loop, so I tried all of them as well. And okay, so summary thus. After these steps, we managed to beat the C++ version. But as you can see, that like there definitely needs to be more. So Go has pretty good concurrency. So let's try that. So going parallel. Parallel performance starts from correctness. If you don't have correct code, it's not worth doing, I guess. And the main ideas that you need to keep in mind while tuning for performance in a concurrent program is that distribution work to different coroutines, threads, cores, machines takes time. Collecting of the results takes time. And don't change data in the same memory location because it ends up clashing between the different workers, and they end up fighting over the cache, which means that the caches cannot do their work properly. And I think if you follow these three ideas, you get a pretty good concurrent code as well. So while I went to sleep after the first day of optimizing this breadth first search, the Slack channel tried the initial implementations to spin up a coroutine for each of the cores on the processor and split it up into equal chunks, and then gather the results through a channel into a single slice. And as a result, on running a program on 48 cores, we made it 10 times slower. So that wasn't great, I guess. You usually expect to make it faster, just to clarify. So why did it happen? So one of the things was that there were some bugs in the code. Of course, that doesn't help things. And the other thing is that if you equally distribute input work for the workers, you don't necessarily know how much time each work item will take. So a single chunk might take significantly longer than some the same size input work, right? So when I split up this current layer, there might be much more nodes to visit in here in the middle part rather than on the sides. So to fight this, you can use a worker pool. Don't do it actually, just you can, but it's usually not a good idea. And then we got to a more reasonable result that's faster at least, but it's still not that fast because we're just slightly improving things. So what we can do is try to distribute our work more evenly or in a smaller chunks. That way, if one of the pieces takes significantly longer than the others, it will still roughly end up equal work for each of the workers. If we do this optimization or change, then we finally get the results that we want or closer to what we want. So we ended up 2 times faster on 4 cores and 4 times faster on 48 cores, which still isn't anywhere close to perfect parallelism. So there were different bottlenecks. One of the things is that we added this sorting to optimize this walk over the nodes. And one of the issues is that we cannot parallelize this easily because distributing this concurrent sorting is difficult. So instead of speeding up things, we would end up slowing things down because the work distribution and collection would be slower. However, there's this old saying that empty programs give the wrong answer in no time at all, which kind of usually means that if you have a bug in Go, if you have wrong code, then you can get the wrong answer really fast, which is actually an interesting thing to think about because on the other side, it's easy to be fast if your code doesn't have to be correct. And for this sorting, one of the interesting things is that it doesn't need to be perfect because we use it as an optimization for iterating through the nodes rather than for the correctness of the algorithm. And if we sort instead of each of these in blocks, rather than the whole slice together, we get multiple sequence of sorted elements. And of course, we notice that, oh, right, we can then, of course, make this assignment to the level parallel as well. And yay. So 10% faster. So, and of course, I continued measuring, and this is what I had. So this set bucket thing was still a bit slow. So I was wondering, what can I do here? What if we kind of do it in bulk? Rather than fetching one bucket at a time, we'll fetch multiple these set buckets to update. As a result, of course, the code readability goes somewhere else, not here at least. And as a result, we got 10% improvement. Whether you really want to do that depends on like what is your actual threshold for performant code and how fast you want to make it in the first place. So also, I started thinking that maybe we can optimize this data the set structure to have a cache, essentially. So multiple levels of cache, maybe that will help. And 10% slower, of course. What would you expect? And I was starting a coroutine every loop. Maybe we can get rid of that somehow. Of course, that started complicated implementation. All things started failing, and I eventually implemented it correctly. However, it was 2 times slower on the large data set and 20% slower on the small data set. Maybe some custom mutex implementation. Terrible idea, I know. Don't hate me for it. Also, don't use it in production. If you do, I will hate you. Yeah, didn't help. 10% slower, 2 times slower as usual. And this is how usually performance optimization stories end, with a bunch of failures. Final results. Single core. We went from 48 seconds to 24 seconds, which beat the C++ implementation. However, I would guess C++ would be faster if we did the exact same optimizations there. And for a 4-core machine, we ended up with 2 times faster than the single-core version. And for the 48-core machine, we ended up with quite a bit faster. So from 48 seconds to 3.8 seconds. And I'm sure there's at least 20% improvement somewhere. I started implementing a radix sort for that and seeing different ways, but I guess that's a story for another time. Thanks for listening, and hopefully you stayed alive during this talk. Thanks. And there are blog posts here for if somebody wants to get into the details.
Thank you so much for your talk. It was super interesting, and I really like the fact that it was very kept to how all the failures that happen when you're doing this, particularly how it ended with so many failures, which means you cannot really optimize anymore.
I think the expectation from outside can be that the performance optimization just happens magically, and you kind of and somebody with a bright mind comes up with a really good solution. But actually, it's just a lot of experiments until you hit the jackpot, I guess.
We do have a question, but Christian said that he will like to take it on the break, so we can keep on schedule.
Yes.
I would like to thank you so much for your talk again, and mention that the charity you chose, I don't know if I did, I don't remember, was Cool Earth. And yes, some people want to share some links of the blog. So we'll be logging off now, and you can go to the group networking sessions in which you're invited and go on the break now.
Yep. Thanks.
Thank you so much.